In the next few videos, we're going to generalize the idea of linear regression just in terms of a straight line data fitting to linear regression in the sense that you can data fit your data to sort of any curve, almost any curve. And the way that we're going to do this is we're going to set up some notation, and we're going to let f1 through fk be linearly independent functions. And what I mean by this is it's the same definition of linear independence of vectors, namely that there does not exist a set of numbers a1 through ak such that when you sum up, so let me just say this, i.e. there does not exist a set of numbers a1 through ak, so these are real numbers, or complex if these are complex valued functions, such that the sum of ai fi equals 0 as a function. So let's just say the domain of our function is whatever we need to specify it to be. For example, the whole real line, or maybe an interval or something like that. So, and imagine you're given data points. And let's say the given data points, again, we're going to use our x and y variables. So your input is x and your output is y. And you have a whole list of data, x1, x2, up to xd, where d is the number of data points. And you want to fit these points to these functions. So in other words, your hope is to somehow fit y1 equals to a1 f1 of x1 plus dot 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 ak f k x1. And not only do you want this, but you also want this to hold for all of your data points. So up to yd a1 f1 xd now plus dot 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 a k f k x d. So this is your hope, but if d is much, much greater than k, then this is unlikely. It's usually impossible to find coefficients that fit all of these data. So before moving on, let's try to rewrite this expression in a linear way so that we can relate it to the linear regression problem we solved earlier. So set y to be this vector here. So let's call this the vector y. And what you notice here is that each of these numbers, so f1, x1 is a specific number, we're taking a linear combination of these numbers with coefficients coming from the a's. So this looks like the vector y1 down to yd. This is what this equation is represented by, a matrix whose entries are given by these values of f. So f1, x1 in the first column, and up to yd, the coefficient in front of a1 is f1, xd. And then this goes up to fk, still x1, so x1 is the first row, and down to fk, xd in the last row. And this matrix is applied to the vector of unknowns, a1 through ak. So this is again of the form y equals a, and let's call it c instead of x to not confuse ourselves with the variable x that we've used for our data. So in general, it's impossible to solve this. And the way that we would like to solve this is, again, a least squares solution. So a least squares solution or approximation to this is a actual solution to A transpose y equals A transpose A C. So just apply A transpose on the left on both sides. And this is generally what we're going to solve for, and this will be fitting our data to the set of functions defined by these. But there are a few restrictions that have to be made. For example, the first maybe obvious restriction, if you think about it, is that these coefficients should be independent. And independent in the sense that I can't take any one of these coefficients and sort of re-express it in terms of the others. I'm not talking about linear independence, I'm just talking about independence. So we assume the coefficients are independent. And this just means, i.e., there does not exist an I from 1 through k such that ai is determined by aj by all the other aj's. So let's just say the set of aj's, where j is now from 1, excluding I, so I wrote a little hat over that to exclude I, up to k. So in other words, in terms of all of the other coefficients. So we assume that they're independent. And this is sort of obvious, right? Because if you wanted to fit your data to these functions and you assume that these were all unknown coefficients and you wanted to find the best value for them, then if you suddenly did that arbitrarily, then it's unlikely that this relationship between them holds in that situation. So in general, we definitely want to make sure these coefficients are independent. Not only that, we also should assume that the functions are linearly independent. So we assume that these functions are independent as well. And this is because, so suppose that one of these actually depended on the other. So because if, let's say, fi equal to some linear combination of the other ones, so let's say bj, fj, so j goes from 1 to k, but j is not equal to I, so we're just saying, like, for these to be linearly independent, another way is saying that at least none of them can be expressed in terms of the other. So if that fails, at least one of them can be expressed in terms of the others. So because if for some numbers bj, then what happens to these expressions? So then if we take f and we take its linear combinations, so let's say ai, sorry, let me not use the index I, let me use the index j now. So let's take sum of aj, fj, and this breaks up into two parts now, right? Because we have a sum over j where j is not equal to I. So this is j not equal to I. And the sum goes from 1 to k. So this is aj, fj. But then we also have plus ai, fi. But this term equals this. So this equals sum over all j not equal to I, another sum over all j that are not equal to I. So we have aj, I'm just copying this term, fj, plus ai times this. So ai times bj, fj. And then this is all in parentheses. And now you notice that fj is a common factor. So when you factor that out, you get sum j not equal to I. And then this is aj plus ai bj fj. So now what we've done is we've re-expressed our linear combination of these functions, so the way everything that's on the right-hand side here in particular, and we've re-expressed it in terms of functions, in terms of k minus 1 functions. And now our coefficients have changed So in other words, there was already a dependence on the coefficients in some sense, and so we usually demand that the functions are linearly independent so that we avoid this issue. In the next video, we'll explain more generally a simple situation that occurs in which this function, this linear system, is always solvable by the method that we used earlier, namely by taking A transpose A inverse.